So this is what I like to call unit arithmetic or unit gymnastics. If we're working with scientific quantities that have units attached to them and we're doing arithmetic or algebra or even transcendental functions with them, then how do we know what happens to those units? Let's start with the example of multiplication and division, because this is the one that we've already done a considerable amount of work with. So let's say I have this expression, k times q divided by r, and I happen to know what the units of k, q, and r all are. Q is a measurement of electrostatic charge, and so it's measured in coulombs, which we'll abbreviate by C. R is a measurement of length in meters. K is this constant that's measured in units of joule meters squared over coulomb squared. So what do we do with those units when we're multiplying and dividing these quantities together? What do the units do? This is the unique situation where when we multiply and divide scientific quantities, their units combine together. Their units correspondingly multiply by one another or divide by one another. And so in our example here, kq over r has units of, that's what I'm going to mean by that little twiddle. So the units of k were this messy joule meter squared over coulomb squared. Q has units of coulombs. R has units of meters. And so the units of this combined quantity are just the combined units of these quantities, combined in the same way that we combine the quantities themselves. And so all we have to do here is just simplify, to the extent that we can, the fractions that are present here. So to do that, I can just take my coulomb squared from this denominator and bring it down to that denominator instead. So that what I'll end up with is, I'll have joules, I'll have meters squared, I'll have coulombs, and then downstairs I'll have a meter, I'll have coulomb squared. Now simplify this simple fraction for me. How many meters do I end up with when the dust settles? How many factors of m? 1. The 2 from on top cancels one of them from on the bottom, and so I end up with just one factor of meters up here. How about coulombs? I end up with 1, but the one that survives is in the denominator. And then my joules are still here on top. So multiplication and division is the unique situation where your units will combine with other units, either by multiplication or by division, and give us new derived units out the end. But what's interesting is what happens to units when we do other arithmetic to them. For instance, what happens when I add or subtract units one from another? Before we look at this example, let's just think of a simpler example. So suppose that my height is 1.91 meters or something like that, and suppose that I take a meter stick and I sort of hold it at the top of my head. That meter stick is presumably 1 meter long. Then the total height that I can reach is the sum, 1.91 plus 1 meters. Now, that numerically is going to be 2.91, but what are the units going to be? If I add 1.91 meters to 1 meter, I'm going to get 2.91 meters. So when we add or subtract units, what happens? What happens to the units in a sum or a difference?
They stay within the dimension that the addition and subtraction was already in.
Yes. So first observation is that the units stay the same. The units are preserved in a sum or a difference. But you also said one other thing. What did the units have to be before we could add or subtract them in the first place? Right. The units must be the same. In other words, we cannot add meters to seconds. We cannot subtract liters from centimeters squared. No. The units must be the same before that happens. It's kind of like when you're working with fractions and thinking about the denominators of fractions. We can add two fractions together if their denominators are equal, just by adding the numerators. But if I have two fractions with unequal denominators, then we can't add them unless we do something else to them. Units are even worse than that, actually. We must have quantities measured in the same units before we can add them together. And when we do add them together, the units stay the same. So looking at this expression down here, 1/2 mv squared plus u. If m is a mass measured in kilograms, v is in meters per second, u is in joules, let's figure out whether we can add this together. By the way, whenever you see just a random numerical constant sitting in an equation, we can almost always assume that that random numerical constant is dimensionless. So we'll do that here. So that 1/2 is not going to contribute to our units. So we're just going to forget about that 1/2. But now m is measured in kilograms. V is measured in meters per second. So I'm going to have meters per second squared. And then U is measured in joules. But looking in our table of derived units, or just thinking back to the last discussion we have, we remember that a joule is a kilogram meter squared per second squared, unit of energy. So does this addition make sense? Can I actually add 1/2 mv squared to U? I'll simplify your units on the left here. Meters per second is being squared as a fraction, and so it's being squared in both numerator and denominator. And sure enough, we can get away with adding these two quantities together because the units are the same. And because the units are the same, when we add them together, first of all, we get something that makes sense in the first place. But second of all, we get something that has units that are the same as the units of each one. So when I add 1/2 mv squared, which has the units of kilogram meter squared per second squared, to U, which also had units of kilogram meter squared per second squared, I'm going to get a sum that has the same units as the original quantities did. So we can't add or subtract unless the units are the same in our two addends. And then when we do add or subtract, the units stay the same. So same units, add them together, units stay the same. Despite appearances, the two examples on the bottom are even simpler. We already talked about one. We already talked a little bit about what happens to units when we take a trigonometric function of them. For instance, in this expression mg sine theta, where m is a mass measured in kilograms, g is an acceleration due to gravity perhaps, measured in meters per second squared, and theta is an angle in radians. What happens to an angle once we take its sine? What will the units of that be? So think again about how the sine of an angle is defined. In a right triangle, it would be the length of the opposite side divided by the length of the hypotenuse of that triangle. But that's going to have units of length divided by length. And when I divide meters by meters, what units does that quotient have? None at all. Sometimes we represent a dimensionless quantity just by the number 1. Because multiplying by 1 is the same as not multiplying at all. So the upshot is, a trigonometric function, once we apply a sine, cosine, or a tangent to an angle, the result is a quantity that's dimensionless, always. Because it's a ratio of two quantities that have the same units, namely both units of length. So the result of applying a trigonometric function is always a dimensionless quantity. And the same is actually also true of exponential and logarithmic expressions. For instance, in this expression we have a quantity p naught, which is maybe the number of thousands of bacteria in a petri dish. Then I have a constant k, called a rate constant, which has units of 1 over seconds. And then t, an amount of time, measured in seconds. So what are the units of this thing going to look like? Well, p naught is going to be measured in thousands of bacteria. That's a unit, even if it's not an SI unit. And then I'm going to be multiplying it by the number e. We're going to talk a lot more about the number e as we go into next week. But raised to the power of negative, and negative is the same as just a -1 as a constant. And since that's a numerical constant, we're going to do the same thing that we did up here, and just consider that to be dimensionless. So we'll just forget about that minus sign in the numerator. And then I've got k, which has units of 1 over seconds, and I have t, which has units of seconds. So what are my seconds going to do up here in the exponent? They're going to cancel. My seconds are gone. And so I'm going to be ultimately taking the exponential of a dimensionless quantity. And when I take the exponential of a dimensionless quantity, I'm going to get something that's also dimensionless. So both of the examples on the bottom row here, both exponential and logarithmic evaluations as well as trigonometric evaluations, those always end up giving you quantities which are dimensionless. So the upshot is exponentials, logs, sines, cosines, tangents, they don't mess with your units at all. They don't affect the units and the expressions that they participate in. It's only going to be those coefficients that multiply exponentials and logs where your units are going to come from. But the exponential of something, the logarithm of something, the sine of something, the cosine of something, the tangent of something, all of those are dimensionless quantities.